Bismillahirrahmanirrahim. So today, inshallah, we're going to discuss our last topic in this course, which is about power amplifiers. Yeah, we have a lot of material to discuss, so let's start. So we're going to start when we talk about power amplifiers by talking about their load lines. We have seen the amplifiers already in the practical. In the second experiment, when we were looking at the applications of transistors, so we saw the buffers and we saw the amplifiers, the common emitter, the common base, and the common collector. Today we're going to talk about them in greater detail. So we'll start by the load line. So the load line is similar to the load line that we have seen for the power regulator. In terms of that, it is a relationship or a graphical representation of the relationship between the current and the voltage, right? And the slope of the curve gives us 1 over R, the 1 over the resistance. Okay, so if we have a transistor, an amplifier, or a transistor, a transistor in general, remember that it can operate in one of 3 modes: cutoff, saturation, or active. So cutoff and saturation, we alternate between them in switching applications, on and off. So saturation is on and cutoff is off, right? Let me just fix this a little bit. Okay. So when we talk about power amplifiers, we are interested in this mode, right? So we're going to be focusing on the active mode. So if you want to have a power amplifier, so the core of the amplifier is the transistor, of course, and we need to make it work in the active mode. So when we talk about the load line, we see how we can actually bias the circuit. What is the condition that we should make the circuit to be at in order to make it work in the active mode. Okay, so the biasing point, or the point at which the transistor or the circuit is going to be biased, is called the operation point, or the Q point. Okay, so in order to make the device, the transistor, work in the active mode, there are different ways, right? I can use as long as because remember, to work in the active mode, there are 2 conditions. We need the BE junction to be forward biased. So if this is my transistors like this, if this is my transistor like this, okay, so this junction has to be forward biased, while this junction has to be reverse biased. So the base emitter junction has to be forward biased, and the collector base junction has to be reverse biased. So of course, there are several ways you can do. There is not a single way. There are several ways you can achieve this. As long as this is true, خلاص, the transistor is in active mode. But the particular point that you are going to be choosing is called the Q point. So let's look at look at this transistor that you have, or the amplifier in front of us in here. So this is a common emitter transistor amplifier. Remember, how can I distinguish whether it's a common emitter or common base or common collector? I will look at the input. So the input is connected to the base. How about the output? The output is connected to the collector side. What is remaining? It's the emitter, so we call it common emitter. So this is not our point here. Our point here is to derive what is the operation point of this device. Now remember, this configuration is called the voltage divider configuration, or VDB. So voltage divider based amplifier. Why is it called that? Because the way I'm biasing these 2 junctions, I'm not using 2 separate sources, although I can do that, but this is not an efficient or practical way to do it. So a much better way to do that is just to use a single DC power supply that we have, like here, the VCC. And using this, it can do both jobs at the same time. It can forward bias this junction, while at the same time reverse bias this junction. How can we do that? By going to this side. Here we have these 2 resistors, R1 or R2. And by applying voltage divider rule, I can have certain voltage appear here and certain voltage appear here. Now this voltage that will appear here, VR2. So this VR2, if I apply KVL, this voltage is equal to what? It's equal to this voltage, VBE, plus VRE. Okay? So this voltage has a direct influence on this voltage. So if I increase this voltage high enough, this voltage will be high enough that it will be forward biased, and it is, in other words, it can be, it will be more than 0.7. So if this voltage from here to here, this voltage, this is BE, right? So this VBE, if it's greater than, if I increase VR2 high enough, VBE is going to be more than 0.7, and this junction will be forward biased. So this is half of the work. The other half is to make this voltage reverse biased. Now remember, this is an NPN transistor. So here I have NPN. Okay, again, I want this to be what? I want it to be reverse biased, meaning I want this voltage from here to here to be more than 0.7, okay? Or in other words, I want this voltage from here to here to be less than minus 0.7, okay? So any voltage less than that is going to achieve, is going to make this reverse biased. How can I do that? Again, by playing with this voltage, this VR1. Now look at this voltage. This voltage from here to here is, if I apply KVL in this loop, it is equal to VRC plus VCB, right? So this is VCB. Okay. So yes, if VCB is, if it is positive, it means this is a reverse biased. So all I have to do is just make this voltage here and make VCB greater than minus 0.7, and the device will be reverse biased. So make it 0 volt, 1 volt, 2 volt, make it something positive to make sure that it's reverse biased. So by doing that, we guarantee that this is reverse biased, this is forward biased, then the device is going to be it's going to be in the active mode. So it can work as an amplifier. Now, as you can see, there are different, how can I now increase this voltage and this voltage, VR1 and VR2? I'm not going to use two separate power supplies, but instead I'm going to use this power supply and then make use of voltage divider rule. Okay, so by playing by voltage divider rule, you know that this VCC is going to be divided between this R1 and R2. It's not going to be divided equally. It's going to be divided based on the value of the resistors, the values of the resistors that they have here. The higher the resistance, the more voltage is going to get. Okay, so my goal is to make this high enough to be forward biased. At the same time, this is reverse biased. This is my goal. So there are several ways. There's not any, right? So several, you can get, as you can guess, there are several ways I can achieve this, right? But some ways are better than the others. So all these ways are some. I can look at them. I can see all the different scenarios in the load line, in the DC load line in particular. Now, if you look at this circuit, I have two kind of power supplies. Or so two sources in general. I have this one, which is the DC power supply, and I have this AC VN here, right? And we said that this VN, the job of this VN, this is basically my input. So this is the signal I'm trying to amplify. This is the useful information, like your voice. If this is like an amplifier inside a microphone, then this is going to be your voice. So your voice is going to be converted to an electrical signal by the microphone. This is your voice. So this simulates your phone, your voice. This is the information. This is to give energy and to bias that transistor to work, because it's not going to work for free. It's not going to do the amplification job for free, right? So this is the purpose of this is to supply the DC voltage to the transistor to work. That's why when I look at biasing the circuit, I'm not interested in this, right? Now my focus now is how can I make this active. So I'm dividing this DC voltage between these things. So I can just ignore this. I can look at the circuit from DC point of view. Okay? So I can look at the circuit from DC point of view. So if I do that, I can actually come here. How does this circuit look in a DC point of view? So I'm going to draw it here. So you know that from a DC point of view, all these capacitors are going to be acting as open circuits, right? As we discussed previously. So this is open circuit, this is open circuit, this is open circuit. Okay, actually the reason why we are adding, let me just bring it to focus again. Okay, the reason we are adding these capacitors in the first place is to isolate the DC, right? So we don't want the DC to appear in the output and affect the input and so on. So from a DC point of view, all these things are going to be open circuits. So how the circuit is going to look like? Here, it's going to look like that. I have my VCC here. Here I have RC connected to the collector of the transistor. Here I have RE. Here I have RC. And here I have my this should be my output connected here, but of course the DC is not going to see the output is not going to reach, sorry, the DC is not going to reach the output because of this coupling capacitor. So it will like an open circuit, so it will block it. So the DC will flow like that, right? Nothing is going to go to the right. And from the left side, here I have R1, and this is connected to the base. And here I have R2, R1. How about from the left side here? I don't have anything. So this is how the circuit looks like from a, we call it DC point of view. So this is how the circuit looks like from a DC point of view. And since this current is almost equal to 0 ampere, then we can say roughly that R1 and R2 are series, right? So the current that we move here is the same, more or less is going to be the same current that will go down here, because this current is almost 0, because this is going to the base. This is the base current. Okay, so this will give us a higher input impedance, and this is a very good feature that we require. Okay, so let me just bring these down here. So now, how am I going to play with the, how can I bias the circuit? I can do one thing. I can just come here, I can make this like a variable resistor, and just play with the value of this resistance. Okay, of course, if I make it 0, if I make if I make R2 0, what's going to happen? Then this voltage will be what? This is basically going to be short circuit. It means all this voltage, which is equal to it, is also going to be equal to 0. If this voltage is equal to 0, معناها this voltage is not equal to 0.7, معناها it's not even active. It's not even on, right? Because VBE is not greater than 0.7. So I need to increase R2 until I reach a point that this is 0.7. Okay? So if R2 is too small, I am in cutoff, because this is not even working in the first place. If I make R2 too small, it is cutoff, because this is going to be, it's not going to be working in the first place. So you can see here, by playing with the value of R2, if R2 is too low, then the device will act like an open circuit, because it's cut off. Again, because this will be easy, according to voltage divider rule, no voltage will be here, 0 volt. معناها here is 0 volt also. All of this is 0 volt. معناها this is not even on, it's off, it's cut off, because I need VBE to be more than 0.7. So at that point, if I talk about this current, because when you talk about the load line issue, it's basically a graph between this current, which is IC, and this voltage, VCE. Okay, and this, so we have IC and VCE. So let's try to draw that. I'm going to plot something like that. Here I have VCE, and here I have IC. I want now to draw the I need to draw the load line. Now this load line, just a second. This load line has two extremes. It is sandwiched between the cutoff and the saturation. When you talk about cutoff, how much is this current is going to be? So during cutoff, this current is going to be equal to 0, because this whole thing is open circuit. خلاص, an open circuit. This open circuit. So no current. معناها IC في حالة الcutoff during cutoff is equal to 0 ampere. Hello? طيب. If no current is moving in the circuit, now this VCC, where is it going to go? يعني لو اتكلمت على VCE في حالة الcutoff. During cutoff, how much is this voltage? Now see, usually this voltage VCC, it is supposed to be given to RC and VCE and RE according to KVL. It's distributed between all these components. But since this is 0 volt, this is 0 volt because the current is 0 ampere, then all this voltage will go to the open circuit as usual. The open circuit will take all the voltage. It means during the cutoff, the VCE voltage is equal to VCC. معناها during cutoff I know what are my conditions. IC equal to 0 and VCE will be VCC في هذه حالة الcutoff. This is one extreme. Now what I'm going to do now, let's go back here. Okay. Now if we start to increase R2, what's going to happen? Eventually, if I increase R2, eventually this will turn on. So eventually I'm not going to be cut off anymore. Now I'm going to the circuit is going to start working as an amplifier because this is forward biased and this is still reverse biased. Now, if I keep increasing R2 high enough, I'm going to reach a point that this is not going to be reverse biased anymore. Actually, this is going to be also forward biased. Okay, so you can see here, if R2 is too large, VB will eventually become larger than VC. This voltage, VB, this voltage will eventually become larger than this voltage. If this is larger than this, and remember this is N and this is P, معناها reverse biased. Okay, sorry, this is N and this is P. Okay, معناها when this voltage is greater than that, معناها it's forward biased. PN. If this voltage is greater than this by 0.7, معناها it is forward biased. If this is forward biased and this is forward biased, معناها saturation. معناها خلاص I'm not active anymore, معناها transistor is not going to amplify anymore. It will saturate. Okay, طيب. So في حالة saturation, I want to talk about the VCC. I want to also talk about the current. So let's start by VCE. So during saturation, how much is this voltage equal to? Remember, in saturation, we said this will act as a short circuit. Man, if it's a short circuit, and remember, it's not actually for short circuit, it should be like 0.2, 0.3 volt, but we say it's short circuit, and for simplicity, we are going to assume it's equal to 0. Man, during saturation, how much is this voltage? Short circuit. Short circuit, man, كم voltage? Man, 0 volt. How about the current? If I want to find the current IC during saturation, how do I get it? Remember, this is a short circuit. هذا short circuit. وعندي VCC. This is the ground, and I have two resistors. معناها simply, I just apply Ohm's law, so it is equal to VCC, voltage هذا, divided by the total resistance, which is what? Which is RC plus RE. So now I have obtained these four values, and then look at these are two. في حالة cutoff, the current is equal to 0, obviously. في حالة saturation, short circuit, معناها voltage is equal to 0. خلاص؟ معناها these are the two values that I have here. So the two extremes of this load line that I'm going to draw now are as follows. First, let's start by the cutoff. So during cutoff, the current is equal to 0. How much is the voltage VCE? So VCE should be equal to VCE. So I'll come here at VCC. So this is the point حقت الcutoff. No current, 0 ampere here, and VCC. طيب. How about the other point, saturation? So in saturation, how much is the voltage? The voltage is equal to 0. معناها I move like that until I go to 0 volt. This is 0 volt. How about the current at that point? The current at that point is equal to VCC divided by this value. So I'll come like that up here. And I'll say this is VCC divided by RC plus RE. Then I draw a straight line between these points like that. So this is your DC load line. This is how you obtain it. You find these values, simple as they are. You just put these 2 points, connect them. Now what does that mean? It means now, as long as as long as you are moving along this line, you are in the active mode. خلاص? This is the active mode. If you reach this point and you move like that, خلاص, you are where? You are in the cutoff point. If you go to the left, you are in saturation. Here you have saturation. Here, let me do it. Here you have cutoff. If you go like that, you go to cutoff. If you go to the left, you go to saturation. In the middle, here is your useful active mode, where the device is going to act as an amplifier. This is where you want to be. طب خلاص, as long as you are here, you can be at any point. Remember we said you have different operation points, but the one that you are working at, خلاص, I'm going to put a value for R2 here. I'm going to select a value. So this value, for example, can make Q here. خلاص, this point is going to be your Q point. Or I can make it exactly in the middle. Put it in the middle here. خلاص, this is we call the Q point. Q stands for quiescent. Quiescent means what? It means like constant, not moving, static. Like DC basically. So quiescent means like DC. Because now we are doing, this is DC, right? So we're not putting any information. The information, your signal coming from here, your voice for example, it's not coming yet. So this is called quiescent, stable, not working. Okay, constant. Not constant, DC. Okay? So I can define this operation point by two things, the voltage and the current. So I can call it VCEQ, and the VCE هذا, this VCEQ, then the voltage that you are working at, the voltage that will appear here. So VCEQ with DC voltage that you are biasing the circuit with, and this current right here, which you can guess is called what? It's called ICQ. So we have VCE quiescent, IC quiescent. Okay, so these are the actual current, DC current moving like that, and actual VCE voltage I'm measuring here. Remember, I can have different scenarios. Yeah, let me put the current here. ICQ. I can work anywhere along like this line. But the one that you are decided to work, the one that you are biasing and operating the circuit at, this is called your Q point. So Q point means the actual point that you are working the transistor at. So let's keep this to the side for a moment. Again, this is how you obtain the DC load line, like it's shown here. This is showing you how to obtain the DC load line. So we already done that. Now we move to the AC load line. What do we do in the AC load line? I'll come here. When I talk about the AC load line, I want to see the same operation, but I'm interested in the AC voltage. And I want to talk about this current, is what IC and AC, because remember here I have two currents. I have IC coming from here and IC coming because of this. Why is this current coming here? Because I can say that IC is equal to beta IB, or IC is equal to GM VCE. Right? We'll talk about this in a moment. So this current that will appear here is going to induce an AC current here. Okay? Now we are interested in the AC. I don't care about the DC that will come from up here. Similarly, I want also to talk about this small voltage, VCE AC, the AC voltage that will appear here. Why is this AC, where is it coming from? It's coming from here. I don't care about this anymore. So I want to ignore this. I want to kill this. Now I want to talk about the AC point of view. So how does the circuit look like from an AC point of view? I can come here. So from my AC point of view, what's going to happen? First of all, we apply this like the superposition theorem. So when I apply the superposition theorem, how do I kill this? How do I ignore this? I make it 0 volt. 0 volt يعني ايش؟ معناها short circuit. So short circuit. And remember, this is actually it's connected like that. This is actually like this, right? This VCC هنا هذه VCC. So if I make it short circuit like that, if I make it 0 volt and short circuit, what happens? It means this point is already connected to the ground. معناها this will be connected to the ground. So let me now redraw this here. I will redraw this AC point of view of the circuit. So from the now, of course, what happens to the capacitors? So remember, from the capacitors from an AC point of view at high enough frequency, how do they act? They act as short circuit, right? So from DC point of view, they act like as an open circuit. From AC point of view, they act as short circuit. So here I have, let me draw the transistor. Here I have the transistor. Okay, so this is RC, and RC is going to be connected to the ground. This is the ground. Here I have R1 also connected to the ground. Here I have R2 also connected to the ground, and from the left the capacitor will be short circuit. So here I have my VN to the ground, and then if I look here, this will go to be short circuit, right? Short circuit, so it will short out RE. So RE is not going to appear anymore. So it will be like this, and then from this side, what do I have? This will, the capacitor will after the short circuit. So here I have my RL. So here is RL. Now if you look carefully, if I look at R1 and R2, what is the relationship between R1 and R2? Remember, from the DC point of view, they were connected in series. But if you look now, if they both start from this point, صح? Both start from this point and both end on the ground. So they are parallel now. They are not series anymore, they're actually parallel. Similarly, if I look here, look at this point. Here I have RC going up, and from the right I have RL starting from this point and both ending on the ground. So these two also are parallel. So I can redraw the circuit like that. See, so if I redraw the circuit, it will look like this. Let me redraw it myself. So this is, you can see here I'm drawing them in parallel. So this is R2, this is R1, this is the base of the transistor. You can see up here I should have two resistors in parallel. So he actually in the book he's actually combining them into single resistor because they're parallel. So they're combining into this small RC, and he's saying that RC is equal to RC هذه parallel مع RL. And instead of separating them into resistors, خلاص he combined them together like that. And how about from this side, from the emitter? The emitter is already connected to the ground, nothing, because RE has been shorted out. So this is the circuit from an AC point of view. This is how the circuit looks like from an AC point of view. خلاص؟ طيب. So this is how it looks like from an AC point of view. But how do I draw the load line? And remember, he's just saying that this is saying how we are getting the, like, how we can get this circuit, and what is RC. So RC again small is RC parallel مع RL. طيب. So now we need to do we need to get the AC load we need to get the AC load line, right? So we need now to get the AC load line. How do I get the AC load line? So here you have the derivation. The derivation is not important to us. We actually are going to use these two equations. Okay. Oh, sorry, these you can say 4 equations or 2 relationships or whatever. Okay. So you can see here, if I go back here, I'm going actually to draw the AC load line on top of the DC load line. This is actually how you should do it. You should draw them both of them together on the same curve. So look here, sure. Now, of course, what do you think? See, sure. I'm going when I small letter, it means ايش? Small letter means it's AC. Capital letter means it's DC. Okay. Type. So IC cutoff. What do you think is going to be when the transistor is cut off here or here? When this transistor is cut off, how much is this current? IC, and this is VCE. Yeah, this is VCE small. Small معناها AC again. When this is cut off معناها open circuit. معناها how much is this current? Zero. So cut off, of course, cut off معناها ما في current أصلا. Regardless of AC, DC or AC, this is 0 ampere. Just like this. Just like the DC load line. طيب. How about VCE saturation? Same. So when this is saturation, when this thing becomes saturation, in saturation mode, معناها it's short circuit. And how much the voltage سواء كان DC أو AC, short circuit معناها 0 volt. 0 volt. So you can see that whether you are AC or DC, saturation, IC cutoff or VCE saturation, they are the same. Simple. Look, they are the same. They are simple to find. Okay. So the only thing that you have to fork out is, and even this is all VCC. Yeah. The only thing that you have to get is this and this. وهنا تحت ال AC are going to be ايش؟ Are going to be VCE in cutoff and IC in saturation. Okay, these are the two things that you have to find. This is 0 volt, this is 0 ampere always. But how do I find VCE cutoff? Look, the equation, the relationship is very similar. This is VCE cutoff, so I'll come here. This is VCE, right? So VCE, the relationship, the equation says that VCE cutoff حقت ال AC, it is actually equal to this plus, so you are going to move like that. It's going to be something. It's going to be starting from here, and then I'm going to move to the right. So it's equal to VCEQ plus some amount. Now this amount is equal to what? This amount is equal to, remember, voltage. How do I get voltage in from using Ohm's law? Voltage equal to H equal to I multiplied by C. So which I am going to use? It's actually going to be ICQ multiplied by RC. ICQ RC. Because I'm doing voltage. Okay, how do I get voltage from Ohm's law? It is IC, right? Like that. But how about IC saturation? Same thing. I will start from here, ICQ. We'll move up like that, move up. So I'll start from ICQ and then I will move up. I move up by how much? I move up by, same thing. I ask myself, IC from almost low, it's equal, I current from almost low equals to what? It's equal to V divided by R, right? So it's equal to V, which V? It is VCEQ divided by R, which R? RC. Okay. فلاحظ هذا بيكون يمين هنا by how much? ICQ multiplied by RC. And IC saturation, it will be above this by how much? By VCEQ divided by RC. لاحظ هنا RC RC, هنا ICQ, هنا VCEQ. Okay, so you need to remember these issues. We need to remember these and these. Okay, these things that we need to remember, and they are easy to remember and memorize. طيب. So usually yes, if we draw it, usually I see VC. If you do that, usually this point will be here. اللي هي VCE cutoff. The VCE cutoff حق AC is going to be somewhere here. So it will be below VCC, of course. Nothing can go beyond the VCC because this is your DC supply. طيب, how about the IC? IC actually is going to exceed that, so it will go up. It will be somewhere here like this. هنا نقطة هي ايش؟ IC saturation. هذا اللي وهنا ايش؟ This is VCE cutoff. AC. So now again I'm going to connect between this and this, and as you are going to do that, you are going to notice that both the AC and DC will always meet in the Q point. So they always meet like that in the Q point. Okay, so this is here I have my AC load line, and this is my DC load line. Okay, so this is how to draw this. Is very important. Just apply these for the DC. This is for the AC. Just apply these two, and you should be fine. Just plug these points here on the graph, connect, you get your load line curve. Yeah, so here are the different steps. Now, how does the amplifier work, Yasha? Again, I'm going to select my Q point along this line, somewhere along this line, right? So let's say here. Now, what's going to happen? This is your DC. Remember, this is the Q point, the quiescent, the DC point. Now, how are we going to amplify your signal? Let me actually come here. Let me draw another one here. Hello. Now here is Ash, and here is my sect. So here I have my AC coming like that. It's connected to so I'm not going to draw the whole thing, okay? Yeah, here I have a capacitor. I'm not going to draw the whole thing. So here I have Ash, here I have VCE, and here I have IC. I have the current coming like that, and this voltage will appear here. Now, if I don't have my AC, if I don't have an AC signal here, this is called the quiescent point. So I'm working here. This is the point I've chosen by playing with the R1, by playing with the value of R2 and biasing everything. This is where I'm working at. This is the DC point of view. Now, when I add my AC signal, this VC is not going to remain the same, right? It is here if it's only DC. Now, when I add the AC, what's going to happen? The voltage is going to increase. If this is increasing, so if this is going up, remember this is going up and down like that, right? It's AC signal, so this is the same will appear here. Look, so it will go up, down, like that. Just follow it. فالvoltage بيروح هنا يمين يروح يسار. Go to the right, go to the left, like that. Same thing for the current, right? Current, same thing. It will, if it moves like that, the current will go down, go up, go down, go up, and so on. And remember, they are oscillating around this point. يزيد عليها ينقص عليها، يزيد عليها ينقص عليها، وهكذا. Okay, so this is fine. If this is the case, you're absolutely okay. But now you can see what's going to happen now. If the Q point is actually not in the middle here, but instead I put it here. لاحظ what's going to happen. And I apply the same signal here. هذه I put it, but the DC is here now. The Q point is not in the middle, it's here. Now what's going to happen? اللي بتلاحظ ان ايش السيجنال we'll try to go like that. But أول ما توصل النقطة هذه, what is the issue with this point? This point is the cutoff. فالفولتج ال AC حقك يركب على الايش DC. When it tries to increase, now the circuit is cut off. So it cannot move anymore. So it will clip like that. See? Clip. See what happened? The signal is clipped. المفروض تطلع هنا وبعدين تنزل. لما ترجع تطلع وتنزل هنا خلاص. Then the signal will continue like that. From this side ما عندي مشكلة because I'm inside the active mode. فما عندي مشكلة here. Go up like that, again clipped. Okay, then it should go up, go down, and then whack. See, signal now is not correct anymore. يعني the amplifier is not actually generating the correct signal because it's clipped from this side. This is called cut-off clipping. This thing is called cut-off clipping. Why is it happening? Because your AC signal is driving the transistor out of the active mode into cut-off mode. So you get something like that, clipped. Cut-off clipping like this. So how do I avoid that? Avoid that by moving away. I shouldn't be here. And this is why am I putting myself just right next to the cutoff? I should move to the left. So I'll move away from this point. So I'll move here. So this is okay. However, how about if I put it here? Now what's going to happen? A very similar behavior is going to happen. If you look at the signal from this part, again, the signal will first increase. And if I apply the same signal, so it will increase, it will go up, it will go down. But now when I reach this point, what's going to happen? Saturation is going to happen. So it's not going to continue. Because here, saturation. The transistor is not, this is the limit. It cannot go to saturation. It's not going to work as saturation. It's not going to amplify. Right? The signal is going to be clipped like this. Go up, go down, like that. So the signal is going to be clipped. See? مقصوصة من هنا. This is called saturation clipping. If I go to the right, cut off. If I go to the left, saturation. So I shouldn't be here or here, right? If I go from here, the positive part of the signal will be clipped. If I move to the left too much, the negative part of the signal will be clipped. Like this, see? The current is clipped, the voltage is clipped. The current is clipped, the voltage is clipped. So now if I ask you, what is the best point you should work? Should you work here or here, next to the cutoff or next to the saturation, or where? Of course, the obvious answer is you should work in the middle. So the best choice is to work the optimal choice of Q, the optimal choice of where you should you should change R2. Okay, you should change your bias circuit such that you're in the middle here, such that you have this full edge. Now you can have all this like as a window for your signal to be amplified without clipping, right? So this is called the optimal value of Q. This is called the AC output compliance. When you put it in the middle, this is called AC output compliance, meaning that the AC is not going to be clipped. Now let's say in general, the signal is here next to the right. See, it's not in the middle. Now, what is the maximum output without clipping that you can have? كم maximum output حقت السيجنال قبل ما أسوي clipping? The maximum is going to be this distance, right? From here to here. Right? طيب, how about if the signal is in the left here? حلو. طبعا which load line we're talking about here? This is ايش? AC load line. This point is what? This is VCE, صح? VCEQ. This point هذه. طب how about what is the end here? Remember it is the end حقت from the relationship that we developed. احنا قلنا النقطة هذه تساوي ايش؟ It's equal to VCEQ زائد this is voltage to apply voltage by the rule, so it's ICQRC. معناها distance هذه من هنا إلى هنا, this distance is equal to ايش؟ ICQRC بس. شوف من هنا إلى هنا it's VCEQ plus ICQRC RC. But بداية من VCEQ لنهاية اللود line, this distance is equal to ICQRC, this alone. معناها this is my limit maximum from this side. طب how about the maximum from this side, from the left side? It's equal to the distance from 0 to this point. طب how much is this point? This point is VCEQ. معناها what's this distance? It is actually VCEQ. معناها when I ask you about any amplifier with a transistor, and I ask you what is the maximum output voltage that you can have without with AC compliance or without having a clipping, so your answer should be what? It should be, it's either going to be equal to this or this, whichever of them is smaller. صح؟ شوف الحالة هذه، لاحظ قيمة ال ICQ RC هذه من هنا لهنا it's large, but the VCQ is ايش؟ small. Which one is going to be limiting? Which one is going to cause clipping? It will be clipped from here faster, earlier, right? Before it reaches this, it will be already clipped from this side. That's why في الحالة هذه VCQ is our this distance اللي هو هذا. شوف الامبليتيود هذا this is your maximum amplitude. طب كم الامبليتيود هذا؟ من 0 إلى الديستانس هذه كم قلنا؟ الارتفاع هذا من هنا إلى هنا is equal to VCQ. But in this case it's the opposite. You can see here قيمة VCEQ is large and ICQ-RC is small. It's only this part. It means it will be clipped from here before this will be clipped. That's why in order to determine, I will say the maximum peak, مش peak to peak, لاحظ maximum peak MP maximum peak is equal to this or this اللي هي المسافة هذه أو المسافة هذه, whichever of them is smaller. If this is smaller معناها هذا هو إيش؟ معناها في الحالة هذه which is the maximum output? This is equal to ICQ-RC. In this circuit, what's the maximum output voltage without clipping? It is equal to VCEQ. So I'll look at the إيش? Whichever is smaller. If I make Q exactly in the middle, what's going to happen? This will be equal to this. It will be exactly in the middle, right? معناها إيش؟ It will be exactly in the middle of the AC load line. معناها these two are going to be equal. معناها هذا is equal to هذا, it doesn't matter. So again, when the Q point is center at the AC load line, be careful, maybe I didn't emphasize this. When you say the center, which load line are we talking about? Are we talking about the DC load line? Should I make it in the center of the AC load line or in the center of the AC load line? It should be in the center of the AC load line. ليش؟ لأن اللود لاين ال AC load line goes to إيش cut off earlier than the DC, right? ال DC يكون في العادة هنا and VCC. So this will go to cut off first. Okay, so you can see when the Q point is in the center of the AC load line, then you can see هذا is equal to المسافة هذه تساوي المسافة هذه. فالموجب is going to be equal to the negative. So they are going to be equal. The positive is equal to the negative. How can I do that? You can make it one way to do it. And this is like an empirical equation. You can apply this equation by making RE equal to RC plus RC divided by VCC divided by VE minus 1. If you just apply this condition, then automatically the Q point will go to the. So you can set all the other parameters, and at the end play with RE such that the device will be in there, or the Q point is going to be them in the middle of the load line. Now let's apply all of that in an example. Here I have example 10.1 from your book. He's asking what are the values, because if you want to draw the load line, as you can see, these parameters are important. I need to know what is ICQ, VCEQ and RC small اللي ايش اللي تساوي RC capital parallel مع RF. So all these parameters are important. We need to get them. So if this is my circuit like that, how do I get these parameters? So these are the substitute foliation. Now I'm going to start with these two, VCEQ and ICQ. So these are DC. So I'll focus at the DC point of view. فأنا عندي هنا DC how much? 30 volt. This 30 volts is divided between R1 and R2. معناها الفولتج هذا هو VB. I can come like that. I can say VB الفولتج هذا from here to here is equal to ايش؟ How can I get it? I apply voltage divider rule. So it's equal to VCC divided by R1 plus VCC multiplied by R2 اللي هي الفولتج هذا divided by ايش؟ R1 plus R2. Voltage divider rule. So if I do that, how much? What do I get? It will be equal to 3.7 volt. And the voltage here is equal to 3.7. If the voltage here is 3.7, man, how much is the voltage here? This is VE. So VE is going to be less than VB by how much? 0.7. So it's equal to 3.7 minus 0.7. So it's equal to 3 volt. Man, the voltage here is equal to 3 volt. If the voltage here is 3 volt and this is VE is equal to 3 volt, then I can get this current. I can say IEQ is equal to ايش؟ is equal to 3 or VE divided by RE. Right? So it's equal to 3 volt divided by 20. So it's equal to ايش؟ 150 milliampere. So this current is equal to 150 milliampere. معناها ICQ is almost equal to ICEQ, right? So it's almost equal to IEQ equal to 150 milliampere. خلاص, we found the first requirement. طيب, now how do I get this voltage اللي هو هذا VC? How do I get this voltage? So I can get this voltage here, VC. VC is equal to what? VC is actually equal to VCC. Remember this current, we already found it, 150. من الفولتج هذا كم يساوي؟ الفولتج هذا يساوي, this voltage is equal to ICQ multiplied by RC. So it's equal to VCC minus ICQ multiplied by RC. Is equal to 30 minus 150 milliampere. How much is this? This is 120. معناها VC is equal to how much? 12, I think. Let me use the calculator. Okay. So 30 minus 0.5, 120. Yeah, 12 volt. Okay, 12 volt. معناها this is 12 volt. This is 9 volt. معناها how much is VCEQ? Sorry, this is 3 volt. Sorry, this is 3 volt. And VCEQ is equal to 12 minus 3 equal to 9 volt. So we know now what is ICQ, we know what is Asia. VCQ and ICQ. So finally we can get RC, very simple. RC is equal to Asia, RC capital parallel with RL. So it's equal to how much? Take these two parallel, 120 180 120. So it's equal to 72 ohms. So we obtained all the required parameters that we need now. All these 3 parameters that we need. Now if we move to the next page, he's asking us determine the AC load line saturation and cutoff points, and also find the maximum peak to peak. انتبه. Okay, we'll do that when we reach it. طيب. So from the AC load line, what do we have? أول شيء IC. Sorry, it should be small letters because it's AC, right? So IC في حالة ايش؟ cutoff. So cutoff معناها current is always 0 ampere without even thinking, right? 0 ampere. طيب VCE في حالة saturation. Again, saturation معناها short circuit معناها 0 volt without thinking. And I need to get these two now. I need to get VCE cutoff. So what do? We said it's equal to VCEQ وزود عليها ايش؟ voltage ohms law says voltage معناها current multiplied by resistance, so it is ICQ RC. How about IC في حالة saturation? Same thing, it is ICQ, start with ICQ بعدين نزيد عليها plus apply voltage ohms law, so it is VCEQ divided by RC. خلاص, this is 0, this is 0, and I have to get this, so we can say that VCE cut off is equal to ايش? Is equal to VCEQ. We just found VCEQ equal to 9, so it's 9 plus ICQ. طلعناها من example اللي راح كم؟ 150, so 0.15 ampere multiplied by RC. RC is 72. See, this is why he's asked us to find this first, because we need these parameters. So this is 275 milliampere. طيب, how about, oh sorry, this is voltage, because I'm taking the answer. Where is it? It's there. If you do that, the answer is 19.8 volt. How about IC saturation in AC? It's equal to ICQ, which is 0.15, plus VCEQ, which is 9, divided by RC, which is equal to 72. This gives us 275 milliamp. طيب, so this is the end of the first part of this topic, power amplifiers. Now let's move to the next one. If I'm skipping any slides, شباب خلاص, you can, يعني they're not required from us. Just follow the ones that I'm explaining now. These are the ones that are required from us. Now there are different classes. We just skipped that. There are different classes of operation, but we are interested in something called the class A operation. معناها ايش? All the signal without clipping is passed. Sometimes we choose to clip negative, sometimes we choose to clip the positive, but usually, يعني the most common case is we want everything to pass. Okay? And you said that the best way is to make the Q point in the middle of the AC load line, of course. So I'll talk about the class A operation. Now again, there is a common emitter amplifier, there's the common base amplifier, there's the common collector amplifier, but the best one and the difference between them depends on the output resistance, right? So it depends on the output resistance. If the output resistance is very high, then it is a good current amplifier, okay? Because we want all the current to go to our device, nothing to be lost inside the amplifier itself. The common emitter has a very low output resistance, okay? So all the voltage will go to the output of the output load. But some common collectors are usually preferred as or the common emitters that want this. So you can see that the common emitter is a good AH voltage, common voltage AH amplifier. Okay, so we're only going to be talking about the voltage amplifier. So we're going to be talking class A and common emitter. So we'll skip the AH class B and class C, and we'll skip the common collector amplifier. So we'll talk only about the common emitter amplifier. So this is the circuit that we have seen already. This is the circuit, the same circuit that we talked about. Again, this is how we can make it without clipping. This is class A operation, nothing is clipped from the signal. Now we need to talk about some of the some of the parameters that we have here. So the first parameter is called the amplification gains. So we have AV. A is usually the gain. So AV معناها voltage gain. What is the voltage gain? It is the V output over V input. How much is the output divided by the input? We have the current gain. It's the output current divided by the input current. And we have the power gain. How much the power has increased in total. So it's P out divided by Pn. Talk about power amplifier. We're interested in knowing also what is that. So these are the two important ones, EV and AP. So in order to find these things, we need to talk about the output power. Now this is an AC signal, okay? When we talk about an AC signal, if we talk about the power, we're interested here in the real power, okay? We're interested in the real power. So if we have the RMS value, so we can find it like that. P out is equal to V out RMS divided by RL square طبعا, of course. V out RMS square divided by RL. حلو. Or because remember what is RMS? V out peak. It's equal to ايش? What's the relationship? It is equal to V. Or let me do it. V out RMS is equal to what? Is equal to V is equal to this divided by ايش? Divided by root 2, right? So V peak divided by root 2. If we square it معناها ايش؟ معناها V out RMS is equal to ايش؟ Is equal to V out peak divided by 2. So you can use that. If you have V out in peak, خلاص you can use this. معناها ايش؟ معناها you can use this equation also. You can say VP out is equal to V out peak square divided by 2RL. You can use that. If B out is square here. If P out is given, if you have it in peak, you can use this. If it is given in RMS, you can use that. If it is given peak to peak, which is usually the case, like you have an oscilloscope or something like that, then it's equal to, because remember, peak to peak, you have to multiply by 2. But here you have square, so it will be 4. So 4 multiplied by 2, because again, V out, it will be like that. V peak to peak is equal to V peak divided by divided by 2. So if I square this will be squared, so here it will be 4. 4 وعندي 2 برا, it will be 8. So this will be this is how we do it if P out is given to you in peak to peak like that. Okay, what is the maximum output power? Again, maximum output power, you can have it MPP square over RL, or you can say it's equal to MP square over 2RL. So you can use this or that. This is the maximum power you can get from your class A amplifier. طيب. Now we'll talk about other parameters. We have the transistor power dissipation. Okay, so when no signal drives the amplifier, معناها ال AC ما في AC, you don't have AC, then the quiescent power dissipation is, what is the PD? PD, the quiescent power dissipation. And power dissipation, the DC part. So it's equal to ايش? It's equal to the DC voltage multiplied by the DC current. Power equal to V multiplied by I, right? So this is how you find the quiescent or the DC power dissipation, or the transistor power dissipation in quiescent mode. So this makes sense. It says that the quiescent power dissipation equals to the DC voltage times the DC current, of course. Now, when you apply an AC signal, now the transistor will work, and it will take some of the DC voltage بتشكله على شكل AC. This is how the amplifier works, right? It will take your input, the weak AC signal, it will look at it, وبعدين بياخذ ال DC, it will take the DC, high DC, وبيشكله على شكل ايش? It will shape it in the shape of the small AC, make it big AC. Okay, that's why this will decrease. Hence, the quiescent power dissipation is the worst case. لما يكون ما عندك ما فيه input signal, this will be the worst case. طيب, we have something called current drain. What's the current drain? It means how much the transistor or the amplifier is going to drain current from the ايش? From the DC voltage here. So we have two currents, two DC currents will come here. عندي هنا DC current هذا اللي هو IR, وعندي ال IC DC, انتبه, capital. So the DC current has two components. The biasing current through resistors. الكرنت هذا لما يمشي داخل الريزستور هذا it will bias it in the active mode. Make again forward bias, reverse bias, whatever. And the current through the transistor. This DC current is called the current drain. Okay? So this current is called the current drain. Why are you interested in the current drain? Because the DC power supplied to the amplifier is equal to ايش? DC power that is supplied into the transistor is how much? Because now I want to talk about the efficiency. The efficiency is what? The efficiency is how much power I'm paying, how much power I'm getting from out. So I need to talk about this power. This power is easy to find. We just talk about how I find this power. So now I need to see how much power this will absorb. In general, not the quiescent, in general. So the DC power is equal to ايش? Equal to VCC multiplied by the drain. What is this drain? Again, this يعني ممكن أقول ايش? It's equal to VCC multiplied by IR plus IC. Okay. Now look, if you look at this circuit, I can actually make this IR small. I can make this small. How can I make these currents? How can I increase the efficiency of the device? How can I make these currents small? Because if this current is small, معناها the supplied power is small. So how do I make this? This is similar to the trick that we did with the power regulator. We're actually going to increase. I can increase R1, R2, RC, and RE while keeping the ratios the same. If I increase them and keep the ratios the same, then I will make them bias. I will make them work where I want, and at the same time, they will achieve high efficiency. So in order to find efficiency, it is P out divided by PDC. And we have seen how to find P out. The equation شفناها من شوي. Yeah, so he's saying that the class A amplifier does not have a high enough efficiency compared to the other amplifiers. So this is not that important to us. Okay. طيب, here we have so this is going to be the last example that we're going to be doing. This is going to be skipped issue. So skip this. Okay, this is going to be the end. This example is the last thing that we're going to cover. So we can put this to the side here. So let's do this example. He's saying that if the peak-to-peak output voltage is 18 volt. Hello? The output peak-to-peak, and V out peak-to-peak is equal to 18 volt. And the input impedance of the base is equal to 100 ohm. Okay, and this circuit, actually, we can draw something called the small signal equivalent circuit. Okay, Actually, this is not accurate 100%, and because of the current circumstance, we're just going to skip it. Okay, so I'm going to modify the example. I'm going to give you the answer right away. So VP out is 18 volt. يعني let's say if VP out is 18 volt and PN هو already طق V out طق PN حسب لك PN ما تحتاج تحسب PN. So PN is equal to 133.7 microwatt. Then find ايش the power gain. If this PN خلاص اعتبر هذا معطى في السؤال. If this is V out and this PN, then how much is the power gain? And let's also find the efficiency. طيب. So first of all, I need to get P out. So P out we said is equal to ايش? If I have peak to peak, then I'm going to say it is equal to V out peak to peak squared divided by 8 RL. Because this is peak to peak. انتبه. Okay, so I'll do that here. So it is 118 square. And usually I ask my students to find all of these parameters, and actually we draw the proper AC equivalent circuit, but we're just going to skip that. I'll assume this is going to given to you directly like this. So 18 squared divided by 8 multiplied by RL is equal to 180. So it's equal to 225 milliwatt. And Pn here is equal to how much? Power اللي هنا, power supplied here, Pn معطاية هنا. So if you want to talk about ال AV, ال voltage gain, كم ال voltage gain? ال voltage gain من 18 peak to peak, sorry, من from 200, it was originally 200 millivolt, يعني 0.2 peak to peak, صارت كم 18 V out على Vn. So how much is that? 18 multiplied by 5, 90. So 90 times. معناها الفولتج صار amplified by 90 times. So how about the AP? How about the power? How much was it amplified by? It's equal to P out divided by Pn. And this is not efficiency. I just want to see how much the power has been amplified, the AC power. So it is 225 milli divided by micro. How much is that? 1683. So 1683. لاحظة يا شباب وحدة الجين ما لها وحدة. Because it's times. How many times? معناها the power has increased by almost 1700 times. Okay, large amount of increase in the, yeah, this is done here. Okay, now let's find the efficiency. The efficiency is continued in the next example. The same example. But the next requirement is to find the transistor power dissipation and efficiency. طيب. So this is the same circuit that we solved in the first. So we know that IEQ is equal to هي نفسها ICQ is equal to ايش؟ ampere 0.15 ampere. وقلنا كمان VCEQ is equal to 9. We already found that already in the first example, right? I can say that PDQ, the quiescent power dissipation, is equal to VCEQ ICQ. So this multiplied by that basically. So we get 1.35 watt. It's a huge amount compared to the milliwatt and microwatt اللي شفناها من شوي. طيب, now if I want to find the PDC, PDC is equal to ايش? PDC is equal to VCE VCC الباور اللي جايه من الباور سبلاي multiplied by IDC. How much is IDC? How much IDC is equal to? It's equal to IR plus IC. Okay. Now we should make these resistors high enough, but in this case they're not that high, right? So this current اللي هو IR, this current اللي هو IR, how do I find it? So IR is equal to this voltage divided by these two resistors in series, right? So it's equal to 30 divided by 490 plus 68. كم يطلع؟ 53.8. 53.8 milliampere. and IC already have found IC. كم ال ICQ كم قلنا 150 milliampere. معناها ال IDC total اللي جاي اللي نازل هنا total current DC نازل من الباور سبلاي is how much? It's equal to this plus that. So it's equal to 150 plus 53.8. So it's equal to 203.8 milliampere. When I have the current هذا now put it multiply it here. So it's equal to 30 volt ضرب here. So 0.2038 gives us how much? Yeah, here. Gives us how much? It's in here already. 6.11 watt. See, huge amount relatively huge amount of power is being supplied by the DC. وكم اللي يوصل للأوتبوت؟ شوف كم واحدة من الأوتبوت؟ less than quarter watt. And if I want to talk about the efficiency, then the efficiency is equal to is equal to P out 100% divided by P DC. So it's equal to, here I have 6.11 watt. Here I have 225 milliwatt divided by multiplied by 100%. So it's equal to only 3.68%. Can you see how small it is? Only 3.68%. Okay, صح ان the power has increased, the AC power has increased, the AC voltage has increased by 90 times, but this is at the cost of huge amount of 6 watt in DC power. يعني كل الباور هذا مستخدم بس عشان تشغل الدائرة inductive mode. How can you improve this efficiency? Again, by increasing these resistors while keeping the ratio the same. So this concludes this discussion about power amplifiers, and it also concludes our discussion about the course in general. So thank you and best of luck inshallah.